Okay guys, in this video we're going to be doing some calculations and I'm going to show you how to use what's called an ICE table for solving chemical equilibrium problems. So in this first example we're just going to learn how to set up the ICE table. And so what you need to do here is you need to copy down the reaction, try to leave some room in between the species. And then what we're going to do is we're going to make the table. Let's see, that would be BR to the fourth. Okay, initial concentrations, change in concentration, equilibrium concentration. ICE. Initial concentration, change in concentration, equilibrium. Sometimes they're called a Rice table. We'll call this the reaction. So let's assume that this problem doesn't specify, but it normally would need to. Let's assume that we've got 1.0 moles per liter of each of our reactants, and initially there's no product. Okay, so we'll say that's 0. Now, some of the reactants are going to react. Okay, so these are going to decrease in concentration. So the change in concentration will make this minus x. Following the stoichiometry, this should be minus 2x. The product concentration is going to increase, and so that should be plus x. Now at equilibrium, the equilibrium concentration is going to be the initial concentration plus whatever change occurred. We've taken into account the signs, and so it would be 1.0 minus x, 1.0 minus 2x, and 0 plus x gives us x. So these expressions here symbolically represent what the equilibrium concentration should be. The value of x, which is called the extent of reaction, is unspecified at this point. We don't know what that is. So, but at equilibrium, x will take on a particular value. And the concentrations of each species are determined by these expressions and what that value is. Here's how you would find it in principle. This is how you would find it, or this is the type of thing that we'll do. We're not ready to do it yet, but I'm just going to show you the types of stuff that we'll do. The equilibrium constant would be known to you. You would set up the equilibrium constant expression. Like so. And then you would substitute in the equilibrium concentration. So it would be x on top. Then you'd have 1 minus x times 1 minus 2x. You'd want to square that. And so that is, what this gives you is a polynomial. This would be a degree 3 polynomial involving x. Assuming that this value of Kc is known, you could solve that polynomial in principle to get the different roots of x. One of the roots is going to be physical. You would then, so you'd solve for x. And then you would take x and you would back substitute it into the equilibrium line. And then that would give you the equilibrium concentrations. Okay, so that's, in a nutshell, that's how these types of problems work. What we want to practice right here is just setting up the ICE table. And so let's skip B because it's too simple. Let's do C. So we'll take, where's this propane here that we're burning with oxygen. It's typically not regarded as an equilibrium reaction. I would think it would be one way, but nevertheless, we can still set up the ICE table for it, even if it doesn't make so much sense to do it. It's good practice. So we'll just assume 1.0 and 1.0 again. It could be whatever the problem tells you. Initially, there's no carbon dioxide or no water vapor. This will be minus x. This will be minus 5x. I'm just following the stoichiometry. Plus 3x, plus 4x. As long as you're consistent with the stoichiometry, that's all that's important. You can really set this up any way you want, but you just need to make sure that everything follows the proportions laid out in the balanced chemical reaction. Add the initial line and the change line together. 1 minus x, 1 minus 5x, 3x, and 4x. Then, and to complete the problem, what you would do is you would set up the Kc expression. So this would be concentration of CO2 cubed, concentration of the water vapor to the 4th power, concentration of the propane, concentration of the oxygen to the 5th power, and then you would substitute in the equilibrium line. So you'd have 3x cubed, 4x to the 4th, all over 1 minus x times 1 minus 5x. That would be to the 5th power. You're going to have this looks like a 7th degree polynomial to me, which is going to be, it's going to have 7 roots. You would need to use a computer to solve that for x. In principle, you can do it. There's nothing particularly challenging about doing that. The computer does all the work for you. And then once you get your value of x, you would substitute it into the equilibrium line, and then that would tell you the equilibrium concentrations. Okay, so here's a whole another set of equations that you can use to help you practice setting up the ice table. We're going to get into some other problems that are related to this, and we'll get some practice, actually solving for the extent of reaction and finding the equilibrium concentrations. So let's see what this problem wants us to do. We want to read it very carefully. So we've got the reaction of iodine and iodide to produce the triiodide ions. If a solution with the concentrations of iodine and iodide both equal 1 times 10 to the minus 3 molar before the reaction gives an equilibrium concentration of iodine of 6.61 times 10 to the minus 4 molar, what is the equilibrium constant for the reaction? Well, it's probably helpful to set up the ice table. Probably don't need it, but just to practice this. So initially, we've got 1 times 10 to the minus 3 and 1 times 10 to the minus 3 for the initial concentrations. We'll take this to be 0. The change line minus x plus x. Add these together. 1 times 10 to the minus 3 minus x, 1 times 10 to the 3 minus x, and x. Now what they're telling us is the equilibrium concentration of iodine is 6.6 times 10 to the minus 4. So what they're telling us is that this number, 1 times 10 to the minus 3 minus x, they are saying that it equals 6.61 times 10 to the minus 4 moles per liter. Then they want us to find the concentrations of the other species. Well, just due to the stoichiometry, if this number is 6.6 times 10 to the minus 6.61 times 10 to the minus 4, then so is this one, right? Because they equal the same expression. So this is also the concentration of the iodide at equilibrium. The concentration of the triiodide will be equal to x, so we need to solve for x. And I'm getting, call it 3.39 times 10 to the minus 4 moles per liter. So I just algebraically rearranged it and solved for the value of x. Okay, and so that is the triiodide concentration. So we could, oops, it's a little too dark. Let me get the light. Likes to automatically go off. So this is equal to the triiodide concentration, and then this is equal to the iodide concentration, which in this problem equals the iodine concentration. So those are the equilibrium concentrations that we found. What else do they want us to do? What is the equilibrium constant for this reaction? So then we would take the equilibrium constant would be Kc I3 minus over I2 iodide. We would then take these numbers and plug them in. So it's going to be the 3.39 times 10 to the minus 4 in the numerator divided by 6.61 times 10 to the minus 4 moles per liter, and that's going to be squared because each of these numbers are the same. So I'm getting 776 for the equilibrium constant. Let's take a look at this one. So we have another reaction here. We've got 1 mole per liter of ethanol and acetic acid. When equilibrium is established when 1/3 of each reactant remains. Calculate the equilibrium constant for this reaction. Well, this is very similar to the problem that we've just done. The difference is that the concentrations initially, so it's actually just 2 reactants. There's 2 products though. 1, 1, and then you'd have 0 and 0. Stoichiometry is all 1 to 1. And then what they're saying is that the equilibrium amounts of the 2 reactants is 1/3. Okay, so I'm going to let you go ahead and try to generalize this problem that we've just done for this problem here. And notice that this is now, this number that I've circled here, the equilibrium concentration of the first reactant, they're saying that that equals 1/3 mole per liter. And ultimately, they want you to calculate the equilibrium constant. I'm thinking this one's probably a little different. So we've got the reaction involving nitrogen and oxygen. They give us the equilibrium constant, and they're asking us to find the nitrogen monoxide concentration given the concentration at equilibrium of nitrogen and oxygen. And so what this problem is going to do, we don't actually need an ice table for this problem. What it highlights is the relationship between the equilibrium constant and the concentrations of the reactants and products at equilibrium. So we have this expression. We know the value of Kc. We know the 2 concentrations here. It's easy to find that one. We just need to rearrange. It'll be Kc into O2 square root. And I think I've worked a problem very similar to this in a previous video. You just take the value for Kc, plug it in. You take the 2 concentrations, plug those in, take the square root. It's going to give you the concentration of nitrogen monoxide in moles per liter. Okay, so this is using the equilibrium constant and equilibrium concentrations to find an unknown equilibrium concentration. Let's see, what do we got here? An equilibrium constant for the reaction of nitrogen and hydrogen. Calculate the equilibrium concentration of ammonia given the reactants. The only difference here is that they want you to actually produce the chemical equation from the words. I think that's good practice for you, but it's the exact same type of problem. Once you get the chemical equation, you write out the expression for Kc, and then you find the unknown concentration. So here's a different problem. Okay, this is one that we want to work carefully. So here we also have to figure out the reaction. So it's the reaction of hydrogen and iodine to produce hydrogen iodide. So it's not too tricky of a reaction. They give us the equilibrium constant. So we know Kc for this equation. It's 50.5. They also tell us the initial concentrations of the reactants, and it's assumed that there's no products. You're probably wondering why I put Cl, IM2. Should be hydrogen iodide. All right, let's set up the ice table, and let's show you how this works. So we've got 1 mole per liter for each of those concentrations. No products initially. Some of the hydrogen is going to react, some of the iodine is going to react. It's 1 to 1, and then that's going to produce twice that amount of product. Add the two lines together to get the equilibrium line. And now we set up the equilibrium constant expression. So it's the products to their stoichiometric coefficients over the reactants. So that's going to be 2x squared over 1 minus x times 1 minus x. And I'll just have you note that that's 2x over 1 minus x. We can write it as squared, like that. So a nice feature about this problem is that both the numerator and the denominator here are squares. So algebraically, this problem is pretty easy to deal with. We know the value of Kc. We need to find the value of x so that we can plug it back into the equilibrium line. Okay. So let's take the square root of both sides. Square root of Kc, square root of a square is 2x times 1 minus x in this case. And then we need to rearrange. Okay, so I'm going to bring the denominator here over. That's going to give me the square root of Kc minus the square root of Kc times x equals 2x. I'm going to go ahead and bring this back over to the other side. So that's going to give me square root of Kc equals square root of Kc times x plus 2x. Factor out the x. And then solve for x. So x will be the square root of Kc over the square root of Kc plus 2. Okay, and we can plug the value of Kc in now. 50.5 square root of 50.5 plus 2. That's going to be our value of x. If I've done everything correctly, I get a value of x equal to 0.78. Let's call it 0. Okay, so there's the value of the extent of reaction. Now, to get the equilibrium concentrations, we plug the value of x in. So the concentration of the hydrogen will equal the concentration of the iodine. It'll be equal to 1 minus 0.78. 0.22, that'll be moles per liter. And then the concentration of the hydrogen iodide will be 2 times 0.780, or 1.56 moles per liter. So these are the equilibrium concentrations. So given the reaction, given the equilibrium constant, using the ice table, we can find the equilibrium concentrations. Well, since it's raining, I'm going to go ahead and break this video up into 2 videos. I just think it'll be too loud over the microphone. So I'm going to go ahead and stop this one right here, and we'll continue to some of the other problems in the next one.